So this is part 2 where I'm going to just do another problem for you. In this problem we have x to the 2/3 times x plus 2. So how I figure out the domain is looking at each piece. So the domain of this guy to the 2/3, so that's an odd root. So my domain for that guy is all real numbers. This guy's domain is also all real numbers. So the domain for this is literally all real numbers. What that tells me is that EVT does not hold because I don't have a closed domain. Things that I do know prior to even starting this problem, that x to the 2/3 tells me that there's a cusp, and the cusp happens at x equal to 0. Now that's useful because I should come out with an undefined derivative at 0. So hopefully if I do the problem right, that will happen. So let's go through our steps. The first step we did, we found our domain. Our second step is to find the derivative. So this is a product rule. I'm going to start with x to the 2/3 times 1 plus x plus 2 times the derivative of the first term, which would have been 2/3 x to the negative 1/3. So what does that really look like? So we are going to write this out a little bit better. X to the 2/3, and over to the right, the negative power I'm going to take to the bottom of the fraction. So that along with the 3, that's the bottom of the fraction. In the numerator, I'm going to keep the 2 times x plus 2. It just makes a lot more sense to do that so you can see that you have a fraction plus something else. And remember I said, so that you can do your sign charts properly and to solve for 0 undefined, you want to have only one fraction. So I can tell by looking at this, I'm going to multiply this term by x to the 1/3 over 3x to the 1/3. So I get 3x to the 2/3 times x to the 1/3. You're going to add the powers, so you actually get x to the 1. Okay. On top here, we still had the 2x plus 2, and the common denominator for both was 3x to the 1/3. So now I'm just going to simplify this guy, and I get 3x plus 2x plus 4, because we have to distribute both, all over 3x to the 1/3. And so off to the right, I get that y prime is equal to 5x plus 4 over 3x to the 1/3. I'm going to set the derivative equal to 0, which tells me that 5x plus 4 is equal to 0. X is equal to negative 4/5. Over to the right, in a lighter color here, I'll do y prime is equal to undefined. That would be where 3x to the 1/3 equals 0. And so x is equal to 0. I have everything I need to be able to do a sign chart. So I'm going to take this guy right here. I'm going to steal that over. And I'm going to use it to make my sign chart. Do it right underneath. And we get, and remember our domain was all real numbers, so I'm going to not have cutoff intervals. I'm going to put in my negative 4/5 here. I'm going to put 0 here. 0 was an undefined, and negative 4/5 was 0. And then we're going to put in our signs. Let's look up top, my derivative. We're going to look at this piece and this piece. So if I substitute in negative 100, the top would be negative, the bottom would also be negative, so it turns it positive. If I substitute in something like negative 1/5, negative 1/5 for the top would cause this to be positive, but the bottom negative, so I get a negative. And if I substitute in any kind of positive number, I would get a positive divided by a positive. So I get a positive. I can tell by looking at this that this would be some type of max, and that this would be some type of min. I'm going to draw in my symbols here. So I go increasing. I flatten out. I decrease. I don't know exactly what's happening here. Well, we do. We know it's a cusp, but just by the sign chart, we wouldn't know. And then we increase. So you can kind of see what's happening here. And just by looking at my arrows, I can tell that this is going to be a local max and a local min. And that's something that I don't think for this problem you would necessarily have to understand. So we have our local max at -4/5, and we have our local min at 0. And if we remember what our original function said, that was x to the 2/3 times x plus 2. So 0, I know the function value is 2. -4/5, I am not going to substitute that in this way. I'm going to go ahead and use my calculator here and go into y equals. We have everything written. So instead of spending time here, I'm going to go vars, y vars, function, parentheses, -4 divided by 5, and press, oopsie, I missed that, huh? So vars over function, pick y1, parentheses, -4 divided by 5, that is not a 5, and then press enter. And if I want to see if that'll turn into a fraction, I can try. So it's 1.034, 1.034. And I will paste in the graph, if I can get it. Oh, did it not come in? Well, I can show the graph, and I'll steal it back over. So here's the graph. Let's see. Let's take this guy. And here we go. So you can see what's happening. You can see that we do have our maximum right around here, which is -4/5. And then we do have our cusp at 0, but apparently I cannot multiply 0 times 2, and that should be 0. So there are our extreme values. Both of them were local. This graph would continue down, and this graph would continue up. So there are only locals in this graph. I hope that this was helpful. And if I have some time, maybe I'll do a third problem where we have a closed domain.